So poroelasticity. And poroelasticity, we use it because everybody uses this term to talk about the coupling between the stress and the strain in solid skeleton of porous materials and the movement of pore water. So if we use the language that we used before, this is actually a combination of two things. So one is the mechanic field, and one for the solid skeleton, one is the hydraulic field. So we put them together, we can call it hydromechanics. But hydromechanics, so the scope of hydrodynamics is broader than poroelasticity. Because poroelasticity, you can see that we have elasticity. We only have elastic for the mechanical part. So hydrodynamics is a broader concept than poroelasticity. But here we only talk about elastic when we are talking about the mechanic field. So now it's just poroelasticity. As I mentioned, the theory of this part could be really complicated, but I want to make it as simple as possible. I want to introduce only the most essential parts that you need to know to understand the theory. This is a classic theory in soil mechanics, in geotechnical engineering, but even for graduate students in geotechnical engineering, it takes them like 1 semester or 1 year. For example, you want graduate students want to do something on it, it takes them 1 semester or 1 year to get a very good understanding of it. So now we are trying to get it done within 2 lectures. So it's very challenging. But again, the good knowledge is that I know this part. I know what is really significant. So I'll just share the most significant part so that you guys don't want to be distracted. But there may be some issue. For example, that is, I try to make it really concise. So I may go through some parts that very quickly, or I may skip some information that I think would be the common sense, but you guys may not know. So let me know if there's some concepts that you cannot understand. So poroelasticity. So first we do it in the same way like what we did in the past one for thermomechanics. So you can see now it's hydromechanics. So it's very similar. So I'm going to talk about the couplings first. And in the previous one, we said that the complete coupling is the two-way couplings. But we just do one way. We just do the coupling from thermal field to mechanic field. For the opposite direction, we do not do anything. We said that one is less common, right? So for this one is two-way couplings, So we cannot skip one. Two-way couplings. And here the coupling is between hydro and mechanical. So it's between the mechanical response of the solid. Here, solid means solid skeleton. And the movement of pore water. So we learned both of them, both parts. And here you can see that we only have solid skeleton and pore water. That means for the porous materials, now it's saturated. So we only have solid and liquid. So there's no gas. And this is first, what's the coupling is about. Second, I will give out the constitutive relationship directly. So this is kind of the key part. So the coupling, between different physical fields, they can occur in different ways. There are two different ways. One way is that the coupling occurs in the constitutive relationships. So between different types of properties, different fields. So that's what we have here for this one. For fluid dynamics, you see that the coupling occurs more on the governing equation level, not from the constitutive relationships. So they're kind of different. So for this one, the coupling starts between different properties, constitutive relationships. So there are it's two-way coupling. So we have two equations. So for the coupling from the liquid to the solid, we have the following thing. Epsilon V. So what's the meaning of epsilon? Strain, right? What about epsilon V? Yeah, the volumetric. When we talk about strain, we have shear movement and we have volume expansion, right? One is just like normal, one is like shear. So they're different. So for stress and strain, we do it in the same way. We can split the stress and the strain into two components. One is normal, one is shear. And normal, one easy way to understand it, just like if you have a balloon, you blow the balloon, you're gonna get the volume change. So that is volumetric stream. It's like the dV over V0, the initial volume, right? So here, and this is one of them, and the other one is like this. So there are two. And in the past, I introduced this before. So if there's no fluid in it, in the past, we have this one. Sigma V equals, this sigma here should be, in the past, we call it sigma M. So here we use sigma. Use a different symbol, but it's the same as sigma here. So it's actually sigma X minus sigma Y plus sigma Z, then divided by 3. It's just like, it's called a mean stress or hydrostatic stress. So you can see that it's just like, now we call it sigma in poroelasticity. The thing is that when you have a balloon, if you compress the balloon with the pressure, you can cause a volume change, right? This one is the relation. K is the proportionality between this pressure on the balloon and the volume change of the balloon. And that's the definition of a K. What is K? Fock modulus, right? Yeah. So, but you can see that now there's a difference. Now you have one more term here. This is for mechanical field only. But this is for, now we have couplings. The reason is that now a change in the stress and change in the pore water pressure, both of them, or either of them, can cause a change in the total volume of the solid. So here, it's the same thing. This eta is defined as it's just like, for example, if we have porous materials, if we squeeze it, if we saturate it, we're going to squeeze some water out, right? So this eta is just like the change, is the water that you collect. You squeeze some water out, so that's the water you collect over the volume, the original volume. So it's just like, it's something similar to this one, this sigma V, but it's for liquid. So now you can see that a change in this sigma and P, both of them, they can cause a change in the deformation. This is kind of a deformation of the pore water. It's just like, we choose, just like, we have a solid, yeah, and we have a liquid, that sit together. Yeah. One thing, one thing move, they will change the other one. And the other thing move, they will change this one as well. Yeah. So that's why it's called coupling. That's why, this is just like, the deformation of the solid, this is deformation of the liquid. And we have any change in P or sigma, they will change, both of them. And they're coupled. But, to give you a clear understanding, let me use something like this. So first, this coupling all these couplings, they only occur in the mean terms, in the mean pressure. So that means they only occur for the normal stress and the normal stream. So usually, for stress and stream, let's do it here. For both stress and stream, we divide them into two components. One is the mean one, or hydrostatic, or both of them. And the other term is called or normal. So this one, deviatoric. So, or shear. So if you want to get a better understanding, in the past, you talk about, for example, stress, you have sigma x, sigma y. So for example, you have sigma x, xx, sigma xy, sigma xz, then sigma yy, sigma zz, then sigma yx, sigma yy, sigma zx, sigma zy. So this is original sigma, right? So I'm just using stress as an example. So why we have these two parts? The reason is that sometimes people want to split into two components. One component is like sigma m, 0, 0, sigma m, and the other part is sigma xx minus sigma m, then sigma xy, and sigma xz, and for the other two, it's the same thing. This is sigma yy minus sigma m, sigma zz minus sigma m. This is sigma yx, sigma yy, sigma zx, sigma zy. Can everybody understand this? So this is it happens a lot in mechanics. The reason is that the hydrostatic part and the deviatoric part, sometimes they are different. For example, when we have polar liquid in solid, the couplings only occurs for the hydrostatic or mean part, not for this deviatoric part. So people want to split these two things. And in our case, again, because it only occurs along the mean parts, so you can see that here we only have sigma v, so epsilon v. So epsilon v is the hydrostatic part for the stream. And the sigma m is the hydrostatic part for stress. So they correspond to each other. And if you want to get a better understanding of what a sigma m is, it's very similar to the p here, to the sigma here, the one that we are working on here. This is sigma m. You can see that. It's just the mean stress. Did I make myself clear enough? So we do this intentionally. The reason is that the water only coupled with the solid for the mean or hydrostatic part of the stress and strain, not the deviatoric or shear part. So we want to split it in two. So for the other one, there's no coupling. We do it in the way that we did before. But for the mean part, now it's different. Because for water, the reason is that for water, you always have the same stress, that is pressure, along all the normal directions. You have P along X direction, the same P along X direction and the Y direction, right? Yeah. That's one thing. Another thing is that when we are talking about statics for water, the water cannot resist the shear, right? So that means it does not control to the shear. And when we talk about dynamics, we need to consider shear. But if we talk about static, there's no time. We don't talk about we usually believe that water cannot resist shear movement. So it does not receive shear movement, so there's no shear stress, there's no shear strain. So we're not coupled with the solid, the shear stress and the shear strain of the solid part. So they're not coupled. So it only controls to the mean or the hydrostatic part. So that's the first thing you guys need to keep in mind. And in order to give you a better idea, what is sigma, or sigma m, and what is epsilon b, what is eta, what is p, what is sigma, what is k and h. So here, let me give you this. Because now we're talking about when we're talking about coupling, we're talking about the mean or the hydrostatic part, right? So for that one, let's go back to the balloon example. Let's say that we have a porous material like this. There's a big balloon. Let's assume that it is a sphere. So in the balloon, we have a lot of particles. So to form a very typical porous material. So this is the porous material. So what's going to happen is that, for example, sigma is just like, if we pull it, if we wrap this porous material up with, one membrane, it's just like a balloon, just like we put some porous materials, particles into a balloon, and then we add water into it, it's that big, it's saturated, then we have this membrane wrapping up, this the porous materials, including both the water and the solid skeleton. So if we say that we put a tensile stress attraction like this, so you can see that this is the attraction. Oops. So cannot go back possibly. Go back from here. Okay, here we go. So this is like a pressure, but it's a tensile stress. So this one is sigma. So sigma acts on this membrane. It pulls the balloon. It's kind of, it's trying to enlarge the balloon and the porous material. So this is sigma. So sigma, you can see that acts on both the solid and the water. So if you have ever learned soil mechanics, this is just like total stress. In soil mechanics, we talk about total stress, effective stress, and pore water pressure, right? It's the same thing, but now it's more complicated. So now sigma, this is total stress. But now again, we're only talking about the hydrostatic part, the mean part. So this is the sigma or sigma m here. Again, this is the total. It's the total stress that we talk about in soil mechanics. And we have another thing. If you insert a pressure sensor into the water, so between the particles we have water, if you put a sensor into it, you can measure here. You can measure that now the pressure is P. So P is that pore water pressure. But here we don't have effective stress here. But you can see that we have total stress, we have pore water pressure. Actually, we can get effect stress later on, but not now. But so what you can see is that we change the total stress, that will cause a deformation. Sigma V is the change in the solid skeleton. It's just like you change in the total volume, because solid skeleton, they represent the total volume of the soil. So if the solid skeleton expands, the total volume it will expand as well. And if you change the pore water pressure, for example, you try to use a pump, increase the pore water pressure, we will enlarge this balloon and the porous materials inside the balloon as well, right? So no matter we increase the value of sigma or V, we're gonna get a volume change like this. So let's say if this is delta V, and then sigma V, epsilon V is delta V over V0. It's the initial. So that's what is epsilon V. And then what is eta? So eta is defined, for example, for eta, if we connect this one, if for the balloon, if let's say if the balloon is not connected, it's not closed, is connect to something, we use a pipe to connect to it. And for the pipe, we use a container here. So if we, for example, if we try to change the P, let's say that, or the sigma, for example, let's say for sigma, so now we reduce the value of sigma, or we try to compress it. We're gonna squeeze some water out, right? We will collect some water. So eta is defined as, so we'll collect some water defined as the water that we collect here, delta VW over V0. It's just like the volumetric stream of the liquid part. And if you want to connect it to something that we did before, it is just the change of theta. Theta is the volumetric water content, right? So this is the original water volume, and this is the original volume of the whole. We know that VW over VW is theta, right? So the change of it is just change of theta. So now you can see the relationship. That is, no matter we change the pool water pressure or the total stress, we're going to cause a change in the stream into the solid skeleton. And here is the same thing. No matter we change the total stress or the pool water pressure, we're going to change this is like the volumetric stream of the liquid. This is like volumetric stream of the solid skeleton. So now they're coupled. Can everybody understand this? This one? Yeah. It's called eta.
Eta.
Yeah.
They are the same.
Here, this is eta. Yeah.
They are the same.
Yes, this is eta. This is definitely. I'm just talking about trying to explain what is eta here.
All right.
So this is the example. You know, you have a balloon and you have porous material inside it. If you squeeze the balloon, we're gonna squeeze some water out. Yeah. So eta is just the change with the water. This delta VW is just the water we collect here over the original volume of the whole porous material. Yeah. And it's based on this one, we know that because VW over VV is theta. So the change of this one is gonna be just the change of theta. So this is the definition of everything. But in order to make it correct, actually we need to know that, you know, this a little bit tricky, because for sigma, we use the convention of mechanics. In mechanics, we say that tensile stress is positive. So for sigma, it's the same thing. If the tensile is pulling the membrane apart, that's positive. But for P, for pressure, we usually say that it's positive when it is compressive, right? It's always compressive, actually. So this is the definition of epsilon V and eta. And before I move on, I want to introduce a few more things. First, epsilon V is just, I introduced this in the previous lecture before. Let me write it down this way. Sigma XX plus sigma YY plus sigma ZZ. I explained this one in previous lecture. And if you still remember the relationship between stream and displacement, you will know that this one just partial ux, partial x plus partial uy, partial y plus partial uz, partial z, right? So how do you write this one using the tensor notation? Nabla and the tensor and the u. So what is this one? How to write this one? Gradient is gradient of u. Gradient is that it will increase the order of. So the gradient of a scalar will be a vector. So it's not a gradient. Divergence, right? Divergence of u. You can see at the dots. This is the condensation or reduced order. This first order, and reduced order by 2. So you get a scalar. And that makes sense. So this is how to get this sigma v. Okay, now you know what is sigma v, and this one I also offer one equation to connect what we're doing today with what we learned before. And you know the meaning of P, you know the meaning, sign convention for P and sigma or sigma m, the total stress, and you know the meaning of eta. So now let's take a look at the meaning of, now you can see that we have K, H, HR. Because if we only have solid, we only have K, right? For the mean part, for the hydrostatic part. We need one more thing. Usually, for example, we said that we needed 2 elastic constants to fully describe the material, a homogeneous isotropic material. But if we are only interested in the mean part, the hydrostatic part, 1 elastic constant is enough. And here, let's keep going to see what is K, H, and R. So K, first, let's take a look at K. So K, we know it is the same as the bulk modulus. So it's defined in this way. So K is defined as K, you can see that here is the change of sigma over the sigma over sigma v, right? And again, this sigma is the mean part, sigma m. And sometimes, we can use the incremental form. So it's also the change of sigma over the change. Here I use this delta to represent the change of something, a small change of something. So in the previous lecture, I used this one. Delta is not very good because, it can be confused with that Laplacian sign. So let's use this sign, delta. This is the variation of delta. So this is the definition of K and its bulk modulus. So what is this relationship between K and E and nu? So Anna, so you just look into it, right?
Yeah, that was E over 3.
3, 1.
1 minus 2 times.
2 nu?
That was okay, yeah.
Okay.
1 minus
2 nu? Okay. Okay, Anna's gave out this one, so it's wrong. Just blame Anna's, not me. So take a look at this one. I'm just kidding. Okay, so it should be like this. So this is K. So we are familiar with Young's modulus and Poisson's ratio, right? We're not familiar with K, but here I just want to give out one equation. Now they're related. They're not independent of each other. So this is K. Let's keep going. And here, actually, if you want to explain more, the meaning of K is that, so it's the same thing. Its meaning of K is that, this happens only when, so if we only have solid phase, this equation is correct. But now if we have water, this one is not correct. We need to place one more condition here. We have this equation valid for definition of K only when P equals 0. So this term, if P equals 0, this term is gone, right? We only have this term. So this definition is correct. Can everybody understand this? So we have both solid and liquid. This definition is not correct because we have another term.
Yeah.
But P. Then I have another question. So what does P equals 0 mean?
No water.
No water, or
Unsaturated.
or we have a valve here. We leave the valve open, right?
Oh.
Right?
Yeah.
We leave it open. If you compress, this whole thing, the water will get out. There will no water. There will be no pressure develop here.
Yeah.
So that condition, we have a name for it. It's called drained in solid mechanics. Some of you took my foundation engineering, you probably heard that before. Drain, undrained, something like that, right?
Yeah.
This is kind of drained. Or another term, some people call it constrained. So this case is, this is not constrained. Constrained is when we say that is there movement or not. But drained means that there's water movement or not. So in this case, it's drained. So K is Bach modulus, but to be more accurate, if there's no solids, we can just use Bach modulus. It's correct. But when there's water, when we talk about porous materials with both solid and liquid, now we need to call it drained Bach modulus. There's another one called undrained. It's different. So drained Bach modulus. So in order to measure it, it's very simple. It's just like, for example, if we have a porous materials has a spherical shape. You compress it, and you let water to be drained out very quickly, and then it's just a relationship between the pressure you put on it and the volumetric strain that you will get. You can measure sigma x, sigma y, and sigma z. You add them up, you get a sigma epsilon x, epsilon y, and epsilon z. You get an epsilon v. You know this one, you get a k. So this is the definition of k. Let me just give me like 1 more minute. Let me finish, this h and k. So h, we define it in the same way, but here usually we use the inverse of h. So the inverse of h is defined as, so let's do h directly. So for h is defined as, you can do it yourself, is a change of p over the change of the volumetric stream, right? Or you can get this one using the first equation. And we need to put a constraint here. What is constraint here? So how to get this one from the first equation? The first term needs to be 0, right? So that we can define it this way. Sigma equals 0. So what does sigma equals 0 mean? There's no pressure on the membrane, right? So we let it deform.
Just caused by that.
Yeah, so this corresponds to another word. That means if there's no stress on the boundary, that means it is unconstrained.
Yeah.
So you can see now you have two things. One is called constrained, one is called drained. There are two things. So drained means that water can get out freely. If it's unconstrained, that means there's no pressure on the boundary. So there are two different things. So this one means unconstrained. And we can also get another definition based on the second equation. So second equation, we have this term here. So we can get another definition. It is the change of sigma over the change of eta. And it also needed to be occurring under the condition that P equals 0. So we get rid of the second term and we get this equation. And based on this equation, we can get this definition. And one more term. That is for this R. But for R, people are used to use the inverse of R instead of R. So for R, is defined, we need to use the second equation, right? Second equation, when you need to set this first term to 0. How do you set this one to 0? sigma equals 0, right? So when sigma equals 0, so this term is defined as the change of eta over the change of p. And it happens when sigma equals 0. That means it's constrained, unconstrained. And we know the meaning of this eta is actually, we can do a little bit of conversion, is just this one. So what is change of water content over the change of pressure? Did we talk about this before? The change of water content over change of pressure? Does it ring a bell? In project 1, did you use something like this? Specific source S sub S, right? Yeah. Now interesting. Now you get the same thing. This is S sub S. This is a quintet, something that we know before. But now we use a different symbol, the inverse of R. Okay, let's stop here.
I think I'm falling for you.